How does a jet engine work? When you board an airline flight, you might not spend much time thinking about the engines, but they're the only reason that 700,000 pounds of aluminum and passengers can hurtle through the air at 80% the speed of sound. So, how do they work? Let's take a look. All jet engines, which are also called gas turbines, work on the same principle. The engine sucks air in at the front with a fan. A compressor raises the pressure of the air. The compressor is made with many blades attached to a shaft. The blades spin at high speed and compress or squeeze the air. The compressed air is then sprayed with fuel and an electric spark lights the mixture. The burning gases expand and blast out through the nozzle at the back of the engine. As the jets of gas shoot backward, the engine and the aircraft are thrust forward. As the hot air is going to the nozzle, it passes through another group of blades called the turbine. The turbine is attached to the same shaft as the compressor. Spinning the turbine causes the compressor to spin. Thrust is the forward force that pushes the engine, and therefore the airplane forward. Sir Isaac Newton discovered that for every action, there is an equal and opposite reaction. An engine uses this principle. The engine takes in a large volume of air. The air is heated and compressed and slowed down. The air is forced through many spinning blades. By mixing this air with jet fuel, the temperature of the air can be as high as 3,000 degrees. The power of the air is used to turn the turbine. Finally, when the air leaves, it pushes backward out of the engine. This causes the plane to move forward. Parts of a jet engine. Fan. The fan is the first component in a turbofan. The large spinning fan sucks in large quantities of air. Most blades of the fan are made of titanium. It then speeds this air up and splits it into two parts. One part continues through the core or center of the engine, where it is acted upon by the other engine components. The second part bypasses the core of the engine. It goes through a duct that surrounds the core to the back of the engine, where it produces much of the force that propels the airplane forward. This cooler air helps to quiet the engine as well as adding thrust to the engine. Compressor. The compressor is the first component in the engine core. The compressor is made up of fans with many blades and attached to a shaft. The compressor squeezes the air that enters it into progressively smaller areas, resulting in an increase in the air pressure. This results in an increase in the energy potential of the air. The squashed air is forced into the combustion chamber. Combustor. In the combustor, the air is mixed with fuel and then ignited. There are as many as 20 nozzles to spray fuel into the airstream. The mixture of air and fuel catches fire. This provides a high-temperature, high-energy airflow. The fuel burns with the oxygen in the compressed air, producing hot, expanding gases. The inside of the combustor is often made of ceramic materials to provide a heat-resistant chamber. Turbine. The high-energy airflow coming out of the combustor goes into the turbine, causing the turbine blades to rotate. The turbines are linked by a shaft to turn the blades in the compressor and to spin the intake fan at the front. This rotation takes some energy from the high-energy flow that is used to drive the fan and the compressor. The gases produced in the combustion chamber move through the turbine and spin its blades. The turbines of the jet spin around thousands of times. They are fixed on shafts which have several sets of ball bearing in between them. Nozzle. The nozzle is the exhaust duct of the engine. This is the engine part, which actually produces the thrust for the plane. The energy-depleted airflow that passed the turbine, in addition to the colder air that bypassed the engine core, produces a force when exiting the nozzle that acts to propel the engine and therefore the airplane forward. The nozzle may be preceded by a mixer, which combines the high-temperature air coming from the engine core with the lower-temperature air that was bypassed in the fan. The mixer helps to make the engine quieter. Types of jet engines. Turbojets. The basic idea of the turbojet engine is simple. Air taken in from an opening in the front of the engine is compressed to 3 to 12 times its original pressure in compressor. Fuel is added to the air and burned in a combustion chamber to raise the temperature of the fluid mixture. The resulting hot air is passed through a turbine, which drives the compressor. If the turbine and compressor are efficient, the pressure at the turbine discharge will be nearly twice the atmospheric pressure, and this excess pressure is sent to the nozzle to produce a high-velocity stream of gas which produces a thrust. The turbojet engine is a reaction engine. In a reaction engine, expanding gases push hard against the front of the engine. The turbojet sucks in air and compresses or squeezes it. The gases flow through the turbine and make it spin. These gases bounce back and shoot out of the rear of the exhaust, pushing the plane forward. Turboprops. A turboprop engine is a jet engine attached to a propeller. The turbine at the back is turned by the hot gases, and this turns a shaft that drives the propeller. Some small airliners and transport aircraft are powered by turboprops. Like the turbojet, the turboprop engine consists of a compressor, combustion chamber, and turbine. The air and gas pressure is used to run the turbine, which then creates power to drive the compressor. Compared with a turbojet engine, the turboprop has better propulsion efficiency at flight speeds below about 500 miles per hour. Turbofans. A turbofan engine has a large fan at the front, which sucks in air. Most of the air flows around the outside of the engine, making it quieter and giving more thrust at low speeds. Most of today's airliners are powered by turbofans. Turboshafts. This is another form of gas turbine engine that operates much like a turboprop system. It does not drive a propeller. Instead, it provides power for a helicopter rotor. The turboshaft engine is designed so that the speed of the helicopter rotor is independent of the rotating speed of the gas generator. This permits the rotor speed to be kept constant even when the speed of the generator is varied to modulate the amount of power produced. How are aircraft tires built? Aircraft tires play a critical role in ensuring the safety and performance of aircraft during takeoff, landing, and ground operations. These tires are engineering marvels designed to withstand extreme conditions, including high speeds, heavy loads, and sudden impacts. The process of manufacturing aircraft tires is a complex interplay of advanced material science, meticulous engineering, and rigorous quality control, reflecting the crucial demands placed on these components in aviation. Aircraft tires differ significantly from those used in other vehicles due to the unique and demanding conditions they face. A typical passenger aircraft, such as a Boeing 737, lands at speeds around 150 to 170 miles per hour and supports a load of approximately 40,000 kilograms per tire. For larger aircraft like the Boeing 777 or Airbus A380, the load and speed requirements are even higher. Aircraft tires must not only absorb the energy of landing, but also maintain structural integrity under these extreme forces. The engineering of aircraft tires involves a detailed understanding of material properties and dynamic forces. Key considerations include load-bearing capacity. Aircraft tires must support significant weight, including the entire mass of the aircraft during landing and ground operations. The tires must absorb the high-impact energy generated during landing without suffering damage or blowouts. The tires must perform reliably at high speeds, often exceeding 170 miles per hour, and in some cases reaching up to 280 miles per hour. Aircraft tires are expected to endure multiple takeoff and landing cycles, often up to 500, without requiring significant maintenance. The tires must function effectively under various weather conditions, including extreme temperatures and precipitation, and resist damage from exposure to sunlight, hydraulic fluids, and other environmental factors. The process of manufacturing aircraft tires can be broadly categorized into several stages. The foundation of aircraft tire manufacturing lies in the preparation of the rubber compound. This involves mixing natural or synthetic rubber with various additives to create a material that can withstand the specific demands of aircraft operations. The precise formulation of the rubber compound can vary depending on the specific requirements of the tire, such as its intended operating speed and load capacity. Initial mixing. The raw rub, burr, and reinforcing agents are combined to create a preliminary mixture. Final mixing. Additional additives, such as plasticizers and vulcanizing agents, are incorporated into the mixture to achieve the desired properties. Cooling and storage. The final rubber compound is cooled and stored in the form of sheets or strips, ready for further processing. Extrusion is used to create the tread and sidewall components of the tire. The rubber compound is heated and forced through a die to create long strips of rubber with a specific cross-sectional profile. These strips are then cut to the desired length and shape. The tread is the part of the tire that comes into direct contact with the runway. It is designed to provide traction and resist wear, and may include features such as grooves to channel water away from the tire during wet conditions. Sidewalls. The sidewall connects the tread to the bead and provides lateral support to the tire. It is typically thicker and more reinforced than the tread to withstand the forces experienced during cornering and landing. The extrusion process ensures that the treads and sidewalls are produced with consistent dimensions and properties, contributing to the overall performance of the tire. Calendering is used to create the casing plies, which provide the structural strength of the tire. In this process, the rubber compound is rolled out into thin sheets and coated onto layers of fabric or steel cords. Casing plies are layers of fabric, often made from materials such as nylon or polyester, that are coated with rubber to improve their strength and elasticity. The plies are then wrapped around the beads to form the core structure of the tire. The calendering process ensures that the casing plies and belts are evenly coated with rubber and free from defects, which is essential for the tire's durability and performance. The various components of the tire are assembled into a cohesive structure in the assembly stage. Placing the casing plies. The casing plies are wrapped around the drum to form the core structure of the tire. Adding the beads. The beads are positioned at the edges of the casing plies and secured in place. Applying the sidewalls. The sidewalls are placed over the casing, plies, and beads, providing additional support and protection. Attaching the treads. The treads are positioned on the outer surface of the tire, where they will come into contact with the runway. Bonding the components. The components are bonded together using heat and pressure, creating a single, unified tire structure. The assembly process requires careful alignment and bonding of the components to ensure that the tire performs as expected, under load, and at high speeds. The curing process is a critical stage in the manufacturing of aircraft tires, as it transforms the assembled components into a durable and elastic final product. This involves heating the tire in a mold under controlled conditions. The curing process typically takes several hours, depending on the size and complexity of the tire. The result is a tire that has the desired strength, elasticity, and surface characteristics.
A final inspection is conducted before the tire is approved for use. This includes a comprehensive review of all test results and visual inspections to confirm that the tire meets all performance and safety standards. The manufacturing of aircraft tires presents several challenges, including the need for materials that can withstand extreme conditions and the requirement for precise engineering. Advances in material science and manufacturing technology continue to drive innovation in this field. The development of new materials such as high-performance synthetic rubbers and reinforcing agents has improved the durability and performance of aircraft tires. These materials offer enhanced resistance to wear, heat, and environmental factors. Innovations in manufacturing techniques such as automated tire building and advanced curing methods have increased the efficiency and consistency of the tire production process. These techniques reduce the risk of defects and improve the overall quality of the tires. Sustainability is an emerging focus in aircraft tire manufacturing, with efforts to reduce waste and improve the recyclability of materials. Aircraft tires are essential components that ensure the safety and performance of aircraft during takeoff, landing, and ground operations. Their ability to withstand extreme forces, high speeds, and harsh environmental conditions is a testament to the skill and expertise of the engineers and technicians involved in their production. As aviation technology continues to evolve, the manufacturing of aircraft tires will remain a key area of innovation and development, driving improvements in safety, performance, and sustainability.
How ejection seats work. U.S. Air Force Captain Scott O'Grady was helping to enforce the no-fly zone over northern Bosnia on June 2, 1995, when a Bosnian Serb surface-to-air missile, SAM, struck his F-16. With the plane disintegrating around him, O'Grady reached down between his knees and grabbed the pull handle of his ejection seat. After a loud bang caused by the canopy separating, O'Grady was blasted into the air along with his seat. Soon after, his parachute deployed, and like 90% of pilots who were forced to eject from their aircraft, O'Grady survived the ejection from his F-16. Following 6 days of evading capture and eating insects for survival, O'Grady was rescued. Most military aircraft, NASA research aircraft, and some small commercial airplanes are equipped with ejection seats to allow pilots to escape from damaged or malfunctioning airplanes. It's important for many types of aircraft to have an ejection seat in case the plane is damaged in battle or during testing, and the pilot has to bail out to save his or her life. Ejection seats are one of the most complex pieces of equipment on any aircraft, and some consist of thousands of parts. The purpose of the ejection seat is simple: to lift the pilot straight out of the aircraft to a safe distance, then deploy a parachute to allow the pilot to land safely on the ground. To understand how an ejection seat works, you must first be familiar with the basic components in any ejection system. Everything has to perform properly in a split second and in a specific sequence to save a pilot's life. If just one piece of critical equipment malfunctions, it could be fatal. Ejection seats are placed into the cockpit and usually attached to rails via a set of rollers on the edges of the seat. During an ejection, these rails guide the seat out of the aircraft at a predetermined angle of ascent. Like any seat, the ejection seat's basic anatomy consists of the bucket, back, and headrest. Everything else is built around these main components. Here are key devices of an ejection seat: catapult, rocket, restraints, and parachute. In the event of an ejection, the catapult fires the seat up the rails, the rocket fires to propel the seat higher, and the parachute opens to allow for a safe landing. In some models, the rocket and catapult are combined into one device. These seats also double as restraint systems for the crew members both during an ejection and during normal operation. Ejection seats are just one part of a larger system called the assisted egress system. Egress means a way out or exit. Another part of the overall egress system is the plane's canopy, which has to be jettisoned prior to the ejection seat being launched from the aircraft. Not all planes have canopies. Those that don't will have escape hatches built into the roof of the plane. These hatches blow just before the ejection seat is activated, giving crew members an escape portal. Seats are activated through different methods. Some have pull handles on the sides or in the middle of the seat. Others are activated when a crew member pulls a face curtain down to cover and protect his or her face. In the next section, you will find out what happens once the seat is activated. When a crew member lifts the pull handle or yanks the face curtain down on the ejection seat, it sets off a chain of events that propels the canopy away from the plane and thrusts the crew members safely out. Ejecting from a plane takes no more than 4 seconds from the time the ejection handle is pulled. The exact amount of time depends on the seat model and the crew member's body weight. Pulling the ejection handle on a seat sets off an explosive cartridge in the catapult gun, launching the ejection seat into the air. As the seat rides up the guide rails, a leg restraint system is activated. These leg restraints are designed to protect the crew member's legs from getting caught or harmed by debris during the ejection. An underseat rocket motor provides the force that lifts the crew member to a safe height. Prior to the ejection system launching, the canopy has to be jettisoned to allow the crew member to escape the cockpit. There are at least 3 ways that the canopy or ceiling of the airplane can be blown to allow the crew member to escape. The seat, parachute, and survival pack are also ejected from the plane along with the crew member. Many seats have a rocket motor fixed underneath the seat. After the seat and crew member have cleared the cockpit, this rocket will lift the crew member another 100 to 200 feet. This added propulsion allows the crew member to clear the tail of the plane. As of January 1998, there had been 463 ejections worldwide using the ACES-2 system, according to the U.S. Air Force. More than 90% of those ejections were successful. There were 42 fatalities. Inside of the plane, a drogue gun in the seat fires a metal slug that pulls a small parachute called a drogue parachute out of the top of the chair. This slows the person's rate of descent and stabilizes the seat's altitude and trajectory. After a specified amount of time, an altitude sensor causes the drogue parachute to pull the main parachute from the pilot's chute pack. At this point, a seat man separator motor fires and the seat falls away from the crew member. The person then falls back to Earth as with any parachute landing. Ejection seat produced by Goodrich Corporation. There are 3 possible ejection modes. The one used is determined by the aircraft's altitude and airspeed at the time of ejection. These 2 parameters are measured by the environmental sensor and recovery sequencer in the back of the ejection seat. The environmental sensor senses the airspeed and altitude of the seat and sends data to the recovery sequencer. When the ejection sequence begins, the seat travels up the guide rails and exposes pitot tubes. Pitot tubes, named for physicist Henri Pitot, are designed to measure air pressure differences to determine the velocity of the air. Data about the airflow is sent to the sequencer, which then selects from the 3 modes of ejections. Ejecting from an airplane is a violent sequence of events that places the human body under an extreme amount of force. The primary factors involved in an aircraft ejection are the force and acceleration of the crew member, according to Martin Herker, a former physics teacher. To determine the force exerted on the person being ejected, we have to look at Newton's second law of motion, which states that the acceleration of an object depends on the force acting upon it and the mass of the object. Initial speed refers to either the climb or the sink rate of the aircraft. It may also be determined by the initial step of the ejection process in a seat that combines an explosive catapult and an underseat rocket. The seat speed must be high enough to allow separation of the seat and person from the aircraft as quickly as possible in order to clear the entire aircraft. The use of an ejection seat is always a last resort when an aircraft is damaged and the pilot has lost control. However, saving the lives of pilots is a higher priority than saving planes, and sometimes an ejection is required in order to save a life.
That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.